Welcome to the next lecture in power electronics. Last lecture we have started our discussions on the introduction and the course structure. In this lecture we will focus our discussion on the power diodes and the switched RLC networks. So the lecture 2 will be divided into different subcategories. So this is the lecture 2A, where we will focus our basic introduction of power diodes and its characteristic. So when we talk about the power electronics, many applications in electronics and electrical engineering involve the diodes. So diodes are basically the fundamental materials or the devices which comes from semiconductors, and these are basically used in the electronics and electrical engineering. Power diodes are crucial in power electronic circuits for electric power conversion. Last lecture also we discussed that the power electronics, one of the basic fundamental requirement is to convert the electric power from one form to the another. So we have seen that power has to be converted from AC to DC or from DC to AC depending upon the requirement. In that applications, the diodes plays a very important role, and since these diodes have higher power rating, we say those to be the power diodes. Function of diodes in power electronics, when we talk about, it act as a switches in rectifiers. So rectifiers are those devices which convert the AC supply to DC supply, and these diodes act as a switch in those rectifiers. It also provides the freewheeling in switching regulators. Last lecture we have discussed a brief overview of the freewheeling diode, where a diode will be connected in parallel with a load, where the load has basically the inductive property, so that the current do not flow in the reverse direction. So the freewheeling diodes are one of the most important application of diodes in power electronics. The reverse charge on capacitors, and it facilitates energy transfer also. So when you have some charges which are present on the capacitors and those has to be removed then the diode plays an important role, and it also facilitates in the energy transfer from one zone to the another zone. It also ensures the voltage isolation between one point to the another point, or the different regions are isolated from each other using the diodes. It also allows the energy feedback from the load to the power source. So when you have the power source which is delivering the energy and you have the load which is consuming the energy, usually the energy flows from the source to the load. Now if you have certain energy which is present in the load in the form of capacitive in nature, that energy can be fed back to the source, and this can be helpful with the use of the diodes. It assists in trapped energy recovery. So whatever the energy that is being trapped in the negative zone when the current becomes negative, so the diode assists in this recovery. This we will discuss in more detail. The characteristic of power diodes often idealized as switches. So basically the diodes act as a switch. Practical diodes have limitations and differ from ideal characteristics. So ideal diodes you will not have any losses, but practical diodes obviously you will have some losses, and its characteristic will be different from the ideal diodes. It possesses higher power, voltage and current handling capabilities compared to the signal diodes. In power electronics, the diodes that we use are power diodes compared to the ordinary semiconductor signal diodes, and hence the power diodes will have high power, it will sustain high voltage, and it has the withstand capability to carry high current. Have lower frequency response or switching speed than signal diode. When we compare power diodes with signal diodes, it will have the lower frequency response. What is the meaning of frequency response? The meaning of frequency response we can talk about in terms of the switching speed at which the diode function. So these all are going to be discussed in much more detail in the coming lectures. When we talk about the components which are used in power electronic circuits, basically the inductors and capacitors are commonly utilized as energy storage elements. So we know that there are two types of elements. One is the active element and another is the passive element. So active elements are those which are basically generating the energy. Passive elements can be the resistors, inductors or capacitors. Here the inductor and capacitor are storing device. It stores energy in the electromagnetic fields, whereas resistor there is a dissipating device. So energy will be dissipated in the resistor in the form of I square R, which is the power loss. Power semiconductor devices control energy transfer in circuits. We have seen that you have to control whatever the energy which are transferring from one part of the circuit to another part or from the input to the output, and these power semiconductor devices do that. We have to understand the switching behavior. It should have a clear comprehension of the circuits having a load RC, RL, LC and RLC circuit. This is very essential. So the first chapter in power electronics, we are focusing our discussion on the switched RLC networks with the help of the diodes. So we will have the diodes and we will also have the loads which are in the form of either RC, RL, LC or RLC. The diodes connected in series with switches demonstrate power device characteristic. So the diodes which are connected in series with some switch will be demonstrating how the power device characteristic are there, because when we close the switch or open the switch, the diode will start functioning, and the diode itself is acting as a switch. So we know that diode conduct only in the one forward direction. So when you have the supply voltage only in the positive half, the diode will conduct, the negative half the diode will not conduct. So it acts as a closed switch, it acts as an open switch in the reverse biased. Analysis of these switching circuit involves the component resistors, inductors and capacitors, whose fundamentals we should know and we have discussed in electric circuits. Diode enables unidirectional current flow. So in the diode, always the current will be flowing in only one direction, and that is from the anode to the cathode. The current cannot flow in the opposite direction, while the switch manages on-off functions. So when you have a switch connected in series, it can be on, that is closed, or it can be off, that is open. Power diode characteristics. A power diode is basically a two-terminal PN junction device. So we have a P-type semiconductor material and N-type semiconductor material. Both are joined together to form a diode which is having two terminals. One is the anode and the other terminal is known as the cathode. The PN junction is formed by the process of alloying, diffusion and epitaxial growth. Modern control techniques in diffusion and epitaxial process ensure desired device characteristic. So whatever the device characteristic we require from the diode, there are different control techniques involved in that, and these control techniques will control the characteristic of that particular diodes. So here we can see that there are two semiconductor material, one is of P-type and another of N-type. Both are making a junction. So here you have the junction P-type and N-type. P-type you will have the positive carriers in majority. In N-types we have the electron or the negative charge carrier as the impurity. When this diode is connected with the battery or the supply voltage in such a way that it is forward biased. Forward biased means the P terminal, P junction will be connected to the positive terminal of the battery. So P of the semiconductor is connected to the positive, the N is connected to the negative. This is forward biased. On the other hand, the reverse biased, the P has to be connected in the negative terminal of the battery and N should be connected in the positive terminal of the battery. Then it will be reverse biased. But diode will conduct only in the forward biased. And then the current will start flowing when it is forward biased, and current will flow from anode to the cathode. Reverse direction, the flow of current is not possible. So this PN junction is basically represented in the form of a diode, and the tail end is represented with a anode, and the head of the arrow is represented by the cathode. Current will flow from anode to cathode when the connection is proper in the forward biased junction. What is the meaning of forward biasing? Forward biasing means that when the anode potential is positive with respect to the cathode. So if you have a diode, now in the diode this terminal is known as anode and this terminal is known as cathode. If the anode is at positive with respect to the cathode which is at negative, then we have the forward biasing and the diode will conduct, current will start flow when the depletion layer potential is crossing by the source voltage. So source voltage should be more than the depletion layer potential, which is usually 0.3 volt and 0.7 volt depending upon which semiconductor material we are using, whether it is silicon or whether it is germanium. A conducting diode has a relatively small forward voltage drop across it, and this is influenced by manufacturing process and junction temperature. So you will be having forward voltage drop because this is a practical diode, and these are dependent on what temperature the junction is operating and what is the manufacturing process involved. When we talk about the reverse biased, now in the diode, for the reverse biased, the anode and the cathode will be connected in the opposite manner. Means anode will be connected to the negative and cathode will be connected to the positive terminal of the battery. So the current will not flow and the diode will act as a reverse biased, or it will act as open switch. Under reverse bias condition, a very small reverse current which is known as the leakage current flows, typically in the range of micro or milliampere. So this current is very less, which is flowing in the reverse bias direction. So this current is known as reverse current under the reverse biasing. The leakage current increases slowly in magnitude with reverse voltage until the avalanche or linear voltage is reached. Now if you applying a voltage, this is positive end and this is negative end, this positive supply voltage will create the forward biasing of the diode, but negative voltage when you are applying, then it is a reverse bias condition. This reverse bias condition will lead to the leakage current, which is I0 in the reverse direction, and if this voltage minus of Vs exceed, the reverse current will also increase till the breakdown occur, which is known as linear voltage breakdown or avalanche breakdown. So here we can see the VI characteristic of a practical diode and the ideal diode. In the ideal diode, the diodes start to conduct at zero potential. So here the potential is zero, but the diode is starting to conduct. And in the reverse bias, you have a diode potential Vd here. But in the practical diode, the diode will conduct after a certain voltage in the forward bias junction, which is 0.3 volt or 0.7 volt. These are the depletion layer potential or the barrier potential known as the knee voltage. Then the diode will conduct. And in the reverse bias, the diode will have the breakdown after a certain reverse voltage minus VR, and then there will be a breakdown of the diode. And these small current which is involved when the potential is negative is known as reverse leakage current. For most practical purpose, a diode can be regarded as an ideal switch. So when we have a diode which is connected in the circuit, it can be represented with a closed switch in the forward bias junction. So it is the ideal switch. Ideal switch means you will not have any losses which is associated with the diode. When we talk about the VI characteristic of any practical diode, it is expressed by one equation which is known as Shockley, given by Shockley, and this is the Shockley diode equation, which is given by the DC state operation current ID, that is the diode current, depends upon IS. IS is the leakage or the reverse saturation current, which is very less in the range of micro or milliampere, then it is e to the power, e stands for exponential, Vd by eta into Vt minus 1. Here the Vd stands for the diode voltage with anode positive with respect to cathode, and eta is basically empirical constant which can be 1 or 2, known as emission coefficient or the ideality factor. This basically is given in the problem whether we have to take 1 or 2. Now one term is here Vt. It is important to know this term Vt. So Vt is the thermal voltage which is given by Kt by Q, where K is the Boltzmann constant given by 1.38 into 10 to the power minus 23 joule per Kelvin, and T is the temperature in degree Kelvin. So if the temperature is given in centigrade, you have to add with 273 to convert that in Kelvin. The Q is the net charge on the electron, which is 1.6 into 10 to the power minus 19 coulomb. Now for an example, if the temperature is at room temperature, that is 25 degrees centigrade, or the ambient temperature, then if we substitute the values of K, the temperature, the charge on the electron, and the constant converting to Kelvin, we get 25.7 millivolt. So this thermal voltage is normally equal to 25.7 millivolt under the normal temperature or the ambient temperature. At any other specified temperature, the leakage current is a constant for a given diode. Leakage current will always be a constant, and these diode characteristics can be divided into three important regions. When the diode voltage is greater than 0, that is under the forward bias region. When the diode voltage is less than 0, that is reverse bias region. And if the diode voltage is less than the minus of the breakdown, that is the breakdown region. Means the maximum reverse voltage that the diode can be applied, that is known as the breakdown reverse biased voltage. The forward bias region, the diode voltage is greater than 0 and the diode current is very small if the diode voltage is less than a specified value, typically 0.7 volt. So since you have the p-type material and n-type material are connected together, a junction is formed. This junction is known as the barrier potential because the p-type is having the majority carriers as the holes, and n-type the majority carriers are the electrons. So these diffusion take place here, or the charge cancel out, which gives to be 0.7 volt. Now if we are applying any potential across the PN junction diode, the supply potential Vd should be more than this 0.7 volt, then only the diode will conduct. The diode conducts fully if the diode voltage is higher than the value of VTD, known as the threshold voltage, cut-in voltage or turn-on voltage. These are given different name, threshold voltage or cut-in voltage or turn-on voltage. So it means that diode voltage should be more than typically 0.7 volt, so that diode can conduct and there is some diode current flowing. Thus the threshold voltage is a voltage at which the diode conduct fully. Means the minimum amount of voltage that the diode has to be applied so that the diode current flows is known as the threshold voltage. Let us consider one example where the diode voltage is 0.1 volt, ideality factor is 1 and the thermal voltage is 25.7. The corresponding diode current, if we want to find out, given by this relationship by Shockley, we substitute the values, we get 47.96 into the reverse saturation current. And approximately this value with an error of 2.1% we have, which is when we substitute the values of different thermal voltage, the value of eta and the supply voltage Vd. Vd increases, the error decreases rapidly. So when you apply the when you supply the voltage and Vd keep on increasing, then the threshold voltage, then this error whatever is 2.1%, which calculation we have taken, because here the voltage is less than 0.7 volt, this error will decrease. And if for Vd greater than 0.1 volt, usually the case Id is more than very greater than the reverse saturation current. The diode current equation can be approximated within 2.1% error using the formula where you can replace this 1 from the equation and you can approximate using this equation. So in the first equation, if you see here, we have in the Shockley equation, we have put -1 also and we get 47.96 is. But in the second equation, we have removed this one term and we are getting 48.96. So if you are not taking this 1, then you will get an error of very less, that is 2.1%. Reverse bias region, the diode voltage is less than 0 and the diode is negative, so that the diode, when very greater than the threshold voltage, this happens when diode voltage is less than 0.1 volt. So here negative indicate the reverse direction. These exponential term in the diode current equation become negligible and small compared to unity. So we can say that ID, that is the diode current, under the reverse biased or the negative zone is equal to minus of Is, which is the reverse saturation current. These indicate that ID in the reverse direction is practically constant and equal to Is. So we can say that ID in the reverse direction of the current, like in this zone, it is practically constant, which is equal to Is magnitude. When we talk about the breakdown region, the reverse voltage is typically very high and often exceeding 1000 volt in the magnitude. So if you are applying any potential to the diode, then the negative potential maximum can be as high than 1000 volt. The reverse voltage may surpass a specified voltage known as the breakdown voltage. So if it is surpassing this voltage, maybe 1000 volt as an example, then there will be a breakdown. A small change in the reverse voltage beyond this breakdown result in indicate in reverse current. So we have seen in the practical condition that there is a reverse saturation current flowing. So this is the current, and here you have the reverse breakdown region. So here you will have a very high current flowing. Operation in the breakdown region is non-destructive if the power dissipation remains within the safe level as specified in the manufacturer dataset. So whenever you are providing a potential in the reverse bias region, you should not reach up to this breakdown voltage, otherwise a heavy current will start flowing in the reverse biased and the diode will break, which is known as the breakdown, avalanche breakdown or linear breakdown. However, it is often necessary to limit the reverse current in the breakdown region to keep the power dissipation within a permissible value. So in the reverse bias condition, there will be a power dissipation and the diode can break. So seeing the manufacturer's data set, we have to see how much the negative voltage minus Vs we have to apply. When we talk about the reverse recovery characteristic, the diode reverse recovery refers to its behavior when transitioning from the conducting to blocking state. So we are moving from a diode which was conducting, now there is blocking state, means the diode is under open switch positions after switching from forward to reverse biased. So when we apply a potential, this is plus Vs or the forward biasing, and when we go to the negative direction, that is minus of Vs, reverse biasing, and the diode will move from conducting to the blocking state, and there the transition which is occurring is known as diode reverse recovery. During regular operation, a diode conducts in the forward bias and block in the reverse bias. We have seen that the diode will act as the closed switch when the anode will be positive and cathode will be negative, which is known as the forward biased. And this is the basic operation of the diode. In the reverse bias, you will act as an open switch and it will block the current. However, there is a brief reverse conduction period. This time period is very brief, small, and there is a reverse conduction period when the switching abruptly from forward to reverse bias known as reverse recovery. It means that suppose you are applying a potential, this is plus Vs, then after a small brief period when this potential is changing its sign from positive to negative, there will be some trapped energy which is known as reverse recovery. Reverse recovery is primarily determined by the time needed. So it is how much time you will be requiring to remove the stored charge carriers. So some energy will be present in the form of charge, which has to be removed when you are going from positive to negative in the diode depletion region, that is known as reverse recovery time. So TRR, reverse recovery time. This should be as minimum as possible. During this time, the diode conducts in the reverse direction, causing a temporary reverse current. So we have seen that the diode is basically conducting in the reverse direction. So here you have the reverse saturation current flowing. Some charges are stored because you are changing the direction of the potential from positive to negative. For a small duration, there is some charge present, and this charge has to be removed from the network, and that time taken is known as the reverse recovery time. Reverse recovery time includes three important components. First, the time to remove the stored charge carrier from the depletion region, crucial for the switching speed of the diode. So TRR, which is the reverse recovery time, it is to be removed, the charges has to be removed from the depletion region. Then only the switching speed will be high. Second, the QRR. QRR stands for the total charge which is flowing during the reverse recovery. It is representing the stored charge from the forward conduction when diode was in operation. Third, the current. The peak reverse current during recovery occurring when the time stored charge is rapidly deleted. So first factor is time, second factor is the charge, and the third factor is the current when the diode is under the reversed bias condition, and this is for very small duration of the time. Manufacturers generally specify this characteristic in their datasheets for application like power supplies and converters to minimize the power loss. They give this information so that the power losses can be minimized. Now let us try to understand when you have a diode and there is a load connected in the diode which is given by R. The supply voltage which you are applying, changing its direction from positive to negative in the reverse bias condition. So we are getting some characteristic. The characteristic B is representing the ideal condition, dynamic characteristic during the turn off, and C is basically the practical condition, dynamic characteristic. So here we can see that the maximum current, this is on the y-axis you have the current and on the x-axis you have time. The maximum current that the diode can have in the forward biased, because it will act as a closed switch, and here the current will be flowing as V1 by R. So V1 by R is the maximum current, and when the time reaches T1, if you see here the T1, then this is the forward bias region. The reverse bias region, what is happening, we will discuss how when the current is becoming negative. Like here, for example, if you see this time zone T1 to T2, which is practically constant here, if you see it, and the reverse current is starting flowing. So the reverse voltage is VR and the resistor is R. Diode is practically off. So you have VR by R as the current flowing, and this is the maximum current. So this is the tapped charge which is there in the diode, which has to be removed. Then the switching speed will increase. So this we will discuss. This is for the ideal condition, and here you have for the practical condition. So if you see the forward voltage which was constant in T1, it is subtracting the losses due to the reverse current, and then you have the negative. So let us see under the practical condition what is happening. If we talk about a time T2, let us see here the time T2. Current is becoming negative. So if you see the current direction, this has become negative and excess charges are removed. So here you have the excess charges which is present. The junction is becoming reverse biased. So if you see here in the time T2, the voltage is now decreased in the negative direction. So it is a reverse biased and rapidly adopt the applied negative voltage. So you are applying a negative voltage in the diode. Equilibrium charge distribution of a non-biased junction is reached. So you have reached equilibrium charge distribution when the biased is changed from forward bias to reverse biased. Now this time zone T2 to T3, if we talk about, there the charge distribution approaches that of reverse bias junction. So the voltage is reverse biased and charge which is present here is basically because of reverse bias. The diode behavior begins to withstand the reverse voltage. Now you are giving a potential minus VR in the reverse bias and diode current drops rapidly to zero. So under the reverse bias condition, the diode current will fall and it will reach to zero. The practical diode, the current reversal delayed due to parasitic inductance. So some parasitic inductance is there. Parasitic inductance which are storing the charges. Reduction rate determined by the lead inductance. How much reduction rate will be there because of the lead, that is the wire which is connecting the diode for the supply. The reverse recovery time, the time taken to current to reverse, crucial parameter in the switching application. So this TRR is very important property when we talk about the switching application, and the interval between T1 and T2 sometimes termed as the stored charge. So when you have the interval we have seen in the waveform T1 to T2, you have the stored charge you have. So here you are giving positive, then the current is moving like this. So this is your T1 and this is your T2. So here you have the stored charge and then you have the charge which is removed. So reverse recovery time we have to calculate. So reverse recovery time is a summation of 2 times TA plus TAB. TA where you are storing the charge. So if you see here the current graph, so it is divided into 2 categories or 2 time zones. One is A where you are having the stored charge and B where you are removing the charges. So here you are removing the charges. So reverse recovery time and reverse recovery current, these equations are important, given by TRR is equal to square root of whatever the charges is stored here, QRR divided by di by dt. This is the general equation of coming from the charge current relationship, whereas the current is given by di by dt into 2 into QRR. So QRR is the reverse recovery charges which is present from the time zone T2 to time zone T3. Let us solve one problem to understand this. The reverse recovery time of a diode is 3 microsecond it is given. Now you can see here the time is very less, 3 microsecond. So in the reverse recovery time, so here you have this zone, the time is very less. And the rate of fall of the diode current is given 30 ampere per microsecond. You have to find the QRR, how much charges is stored in the reverse, and what is the current which is stored in the reverse current. So the given data TRR and di by dt will be useful in finding the QRR and IRR equation. So here you can put it in the QRR equation which is discussed previously and in the IRR equation, and you can find out how much charge, that is 135 microcoulomb in this case, substituting the value of 3 microsecond and 30 ampere per microsecond, you are getting 135 microcoulomb as the net charge which is present in the reverse recovery. Whereas the current, if we are estimating, this is on and less 90 ampere coming, substituting the values of the charge and the fall of the current di by dt. So in this lecture we have focused little bit on the characteristic of the diodes in the forward and the reverse bias condition. We have seen the reverse recovery time and the charges. In the coming lectures, for the lecture number 2, we will focus our discussion on different types of circuits having RL, RC, RLC along with the diodes, which is known as the switched RLC network. Thank you for now. See you in the next lecture.